Hello, friends. This is Shrimoy, and I am a student of VIT University 14 BEC 0277. And I am going to explain analog converter and digital to analog converter. This is an assignment given to us by Professor Karthikeyan sir under EC 304 microcontroller and applications. So I will be telling you about the introduction of analog to digital converter, and then my friend Sanjana will tell you about the interfacing of 8051 with our ADC 0804. So let us carry on with the introductions. So what is analog to digital converter basically? Analog to digital converter is your like everything in environment atmosphere is analog in nature, be it noise, temperature, and but the computer system takes on digital values, so we need to have an analog to digital converter to convert whatever analog values we get from the outside world to the computer. So also there are two very important crucial factors when considered ADC. That is, one is the conversion time and the other is resolution. Resolution can be 16:8, 32, but the higher the resolution, the smaller step size, which is very important. And conversion time is time required to convert analog to digital data, and that is also a very crucial factor when considered for an ADC. So now we are going to look forward to the ADC we are going to use in the program, assembly program, that is our ADC 0804. So a 0804, as it is mentioned, is an 8-bit successive approximation analog to digital converter from National Semiconductors. The most important factor is it has 0 to 5 volt input voltage range, no zero adjustment, built-in clock generator, which is an important factor because it has built-in clock generator. We don't need an external clock generator. Reference voltage can be externally adjusted. So that is for your ADC 0804. Next, we move on to the pin diagram of 0804. So the pin diagram of 0804, as you can see in the diagram, is the first pin consists of CS, which is your first pin, CS pin, which if you put it to zero, you will be able to activate the chip. So chip select, that is CS, should be put to zero to activate the rest of the pins, and the read pin is actually after write. So the write pin is used to start the conversion. A low to high signal is given, and the read pin is used to give that and to give the move that signal, the converted signal, to the output. And we have the rest of the signal, that is B plus, B reference, and B in minus, B in plus, and most importantly this DB0 to DB7, which is connected directly to the microcontroller and processor 8051. So this is for a pin diagram. The pins will be very systematically and very progressively explained later on in the slide. Okay, so now we know that CS, when it is moved, like when to activate the pin diagram, CS should always be considered low. So if we put CS is equal to low, that is 0, the other pins of the ADC 0804 will be activated. And read is like it is an input signal considered, and it is active when it is low. So similar to CS, we have to make it 0 to activate it. It holds, like it gets the converted data, and it's out of the ADC chip. And when a CS is equal to 0, a high to low pin is applied to the RD pin, which is opposite to the WR pin, where low to high output is given. So for third pin, that is WR right pin, it is to inform the processor that to start the conversion. For WR, low to high transition is given to tell the processor to start the conversion process. Clock in and clock out, as you know, is used to set the frequency, the fourth and the 19th bit. And also the interrupt is a very important a pin out here because it is used to indicate the end of conversion. So and to give the volts, VCC is there, or VREF when 0 to for VCC actually when it comes to 0804 it is only 0 to 5 volts voltage. For apart from that, if you have to consider apart from this the other voltages in the section, then you have to go for VREF by 2. Just as I mentioned on the functions of the pin selectors, you can see uh, the function of chip select, read, write, and other options. And ground, as you can know, is the 8th pin. We just need to ground it. And the VCC, as I was talking about, VCC or VREF by 2, whatever is it, is set to 5 volts. Otherwise, out of the section, use VREF. And to provide the input, that is an important fact, to provide the input, the analog input, we use V in plus or V in minus. Now, how do we connect the 8 like A0804 ADC externally with 8051? 8051 has 3 ports, P0, P1, P2, and like we can connect it, we can interface P1 as an input port and connect it with the 7 ports of ADC directly, and use the other port. Here it is set P0, P0 as is connected to the LED to show the output. So the analog signal which is connected to the input is converted to binary output by P0, and which of the LED sections which is bright is set to be 1, otherwise it is 0. So, and when the frequency is high, we need to cut off the frequency, which is done usually by capacitor potentiometers and capacitors potentiometers, or maybe also resistors. So as this you can see, this resistor capacitor RC network will cut off the frequency, and in this case potential will do that job. And here 5 volts is applied, as you can see, which is the maximum voltage you can apply to VCC. And since VSA is 5 volts, we don't need VREF by 2, and that is what is how do we interface it. So when we provide V in 5 volts, all LED will glow indicating all our FFFF, that is two, like all the LED will glow 1111, that is equivalent of 255 in decimal. So that is what is interfacing of 0804 ADC with 8051 microcontroller. And thank you for listening to me. And the next part of the section, that is the program assembly program of ADC 0804 will be explained to you by my fellow friend Sanjeev.
Hello friends, this is Sanjana, 14BEC0264, studying in the same university as mentioned before. My friend Srimoyi must have already explained to you what ADC actually means, how it works, the pin configurations, and the rest of the things. Now I'll be explaining you how to go with the procedure. Basically, here we are been using the Keel software Microvision version 5, and we are executing all the programs on it. Now I'll be telling you the basic procedure of how to go about with the product. How to go about with the flow of the procedure, and basically all the pins are to be configured in a certain way for the program to work. So let's go with it. Here we are basically making SCS is equal to 0. CS is very important to be 0 for the procedure to start. Now we need to give a low to high pulse to WR for the conversion to start. Always remember, it's always a low to high pulse for the WR, and it's always a high to low pulse for the read signal. Now we are going with the interrupt pin. The interrupt pin will always be 1 if the conversion is not finished. So basically, in the process of the conversion, the interrupt pin will be 1. As soon as your interrupt pin will be 0, it means your conversion is finished. So basically, the entire procedure can be summed up into 3 parts. CS should be 0, and a low to high pulse should be given to the WR for the start of the conversion. The interrupt pin will be 1 if the conversion is not finished, and the interrupt pin will be 0 if it is finished. And the pulse that is for the read signal, you should be giving a high to low pulse for the read signal to get the data and display it. Now let's go on with the program. The first line is, of course, the pseudo instruction, the assembly directive. Now we are giving the bit P2.7, the port P2.7, the interrupt. Now we are equating my data with P1, which basically means any data that you will be giving to P1 will be accessed as my data in the further program. Now we are giving 0FF as the value to P1. 0FF, as you know, can be used as a instruction that can just make P1 your input pin. Now, as you know, your interrupt has to be 1 for the program to start. So we are basically setting your interrupt. And what was the second thing we had to do? We had to give a low to high pulse to the WR. So we are clearing the WR and then setting it again. We are clearing the read button because we don't need it at the moment. Now we are like in the accumulator, you're passing the value of my data. Two ACALL functions. One is conversion and data display, which will be explained further. Conversion will be basically we will be using an ASCII to hex conversion, and in data display you will be explained further. The conversion. What was the basic ASCII conversion? You are just moving my data into accumulator again. There are 3 steps for an ASCII conversion. You subtract your data from 0AH and now you check if there is a borrow. How do you check if there is a borrow? You see the carry. So if there is a carry, then you add 30 to the data, and if there is no carry, you add 37 to the data. This is how your ASCII to hex conversion is done, and you will be getting a result, and that result is what's the data to be displayed. So now this is a normal data display program. You're just moving the values which you got after the ASCII to hex conversion into your port P1, since that will be configured as your output port at the moment. For this conversion, for this data display, you're using a simple delay program, not a timer delay program, a simple delay program. We're just setting a timer, a counter. R5 is equal to 5, and we're using a decrement and jump not 0 function for the delay program. As soon as the delay program would be over, your result will be displayed. This would be your result. Your port 1 is basically configured as your output pin, and your output is being displayed. What is the basic difference between a serial and a parallel configuration? A serial configuration will give you the analog to digital converted data into a single pin. But since you're using a parallel IC here, which is basically your ACD 0804 here, then in this one, you will be accessing all the 8 pins of the port 1 for the result to be displayed. Now my friend Shailaja will be explaining you the process of DAC, how it works and its configurations and how the procedure is done.
Hello everyone, I'm Shailaja, 14BEC0216, and I'm going to explain to you how a digital to analog converter works and how to interface DAC0808 with microcontroller 8051. So as you all know, a digital to analog converter simply converts a digital signal into an analog signal. So there are 2 methods of devising a DAC. Method 1 being R2R ladder, the next one being binary weighted resistor. So the R2R ladder concept is preferred because it gives us higher precision than binary weighted resistor. And as I have already said, so in this presentation we will move along with how the basics of how a DAC works and interfacing DAC 0808 with microcontroller 8051. So this is how an R2R ladder is simulated. So you have 2 resistance values R and 2R, and they are configured in such a way that there are 8 digital inputs from D0 to D7, D0 being the least significant bit and D7 being the most significant bit. So R2R, the name comes from the 2 types of resistances that we use, R and 2R. And here we are going to use it is the same principle that is being used in our digital to analog converter 0808, which we are going to interface with microcontroller 8051. And it is also important to note that we are going to use an 8-bit DAC 0808 because we use an 8-bit microcontroller 8051. And before moving on, there are also 2 important things that we need to remember about how an R2R ladder works. if you could remember the points that you had learnt in analog circuit design, there are two important things. That is, when you can refer to the diagram, the resistance between any one node and the ground always remains 2R. That is, resistance R can be whatever value you give, but the total resistance between the node and the ground always remains 2R. And the output voltage or the output current, that voltage we'll speak about later, the output current that you obtain out of the circuit is the weighted sum of digital inputs. So that means your MSB bit has more significance over your output than your least significant bit. So if you need to verify that, assume that your most significant bit is 1 and all other bits are grounded. That is, your MSB bit is connected to VCC. In such a case, if you can calculate the equivalent resistances and the output current, and if your output current is taken to be 2 milliampere, as in this case, you can see that the output current is approximately your reference current divided by 2. In the second case, if you are going to take your D6th bit, the bit next to your MSB, to be 1 and all other bits are grounded, then your output current will nothing but be I reference by 4. So as you keep moving towards the LSB, the significance of the bit to the output current decreases. So that is what the second point means. So I reference here is taken to be 2 milliampere, and if you can calculate, when D7 bit is 1, all other bits are turned to 0, your output current will nothing be but I reference divided by 2. Now what we need is the output in terms of voltage, but the output that you get out of an R2R ladder, that is in DAC 0808, is current. So in order to convert a current into the voltage, all we need to do is have a resistor in between. So what we do here is that we connect an operational amplifier, a well-known operational amplifier to you all, IC741, towards the end, so that the output current from your DAC gets converted into voltage. So if you can calculate the voltage, that becomes V out, or here it's given as VA. VA is equal to VR. VR, where VR is your reference voltage, if you can take it commonly outside. So it varies 2 powers of 2. So N here is equal to 8 because we are using an R2R ladder which is of 8 bits. Some DACs also use Zener diodes, so for example LM336, to avoid voltage fluctuations associated with the power supply. So given here is the circuit diagram of interfacing of DAC 0808 with microcontroller AT51. As you can see, digital input is given from AT51 to DAC 0808 via port 1. So the port pins are given as pin P1.0 to P1.7. So as you can see, P1.0 is connected to D0 of DAC 0808 and P1.7 is connected to MSB D7 respectively. DAC is also connected to VCC of 5 volt, and if you can closely observe, the I reference is given as 2 milliampere if you can calculate the value from the given voltage and resistance values. I have already mentioned that the output of DAC 0808 is in the form of current, so we need it in the form of voltage. So all we have to do is to attach an operational amplifier at the output port. So here we have simply used IC741 with a feedback resistance of value R, such that we get an output in the form of voltage. So let us see a program by which we will understand how digital input is being converted by DAC 0808 into an analog output. So the program specification is that there is a switch which is actually port 0.0, and when the switch is equal to 1, that is the value at P0.0, if it is 0, the DAC output must be a staircase waveform, and when the switch is 1, the DAC output must give us a triangular waveform. So let's move on to the program. So this is an assembly language program that I had run on Keel Microvision. You can do the same and check out for the outputs. So I have configured SW as port 0.0, and the second instruction being an assembly directive that tells Keel software where to start the program. So that is org000h. The third instruction, I am clearing SW. So that means my P0.0 is equal to 1. You can also give set B SW in such a way that your P0.0 becomes 1. So you can execute both of the cases and check out for the outputs. Now the fourth instruction is check move C, SW. So this says that you have to move the value that is in port 0.0 to carry. And the next line, instruction number 5, JC to triangle. So jump on carry to triangle. So the specification was when SW was 1, the output of the DAC was to be an analog triangular waveform. So what happens is the control moves from instruction number 5 to instruction number 14. So triangle is a subroutine. So it says move to accumulator the value of 0, and in the 15th line it says INCR, that is increment, move P1, A. So what we do is we move the value of 0 to port 1 of microcontroller 8051. So basically we configure port 1 as an output port. Now the next line, instruction number 16, we increment A, that is A becomes 1 now, and in instruction number 17 we compare value of A with the number 255. If compare and jump on not equal to increment, so 1 does not equal 255, so the control will again jump to instruction number 15, and this process will continue until A becomes 255, that is A equals 255. So as you can see, this gives you the increasing transition of a triangular wave. So once this loop ends, we go to the next loop, decrement, move P1, A. So now A equals 255. So that means you have simulated the increasing transition of a triangular wave. Now you need to simulate the decreasing transition of a triangular wave. So the maximum value now being 255, so you need to down count from 255 to 0. So what you do is move P1, A. You keep decrementing A by 1 till the time where your A becomes 0. So you use the instruction CJNE compare and jump on not equal to 0, and you keep decrementing. So this loop goes on and on until A becomes 0, and then you have a short jump to check. So we use a short jump because all these were labels, and we move on to check if what the value of SW actually is. So since SW was 1, we had to generate a triangular wave. So it moves to check. So if you had given, now in this program we had given clear SW, so that means SW was 0. So in such a case, your fifth instruction would not have been executed. Instead, the instruction will be executed from the instruction number 6 onwards. So what you do is you move the value 0 to accumulator A, and you label it as start, and you also move the value 0 to P1, so which means you're configuring P1 as an output port, and you call a delay. So a delay subroutine is called. So this is again one of the loops where you introduce a delay. So you move 20 to register R1, 200 to register R2, and you decrement R2 until it becomes 0 and stay in the same loop. And as you can see, instruction 26 and 27, you decrease R1 and you repeat the same cycle, and again you decrease R0 and repeat the same loop. So which means it is a nested loop, and the loop keeps continuing for 20 into 200. So that means 4000 times this loop runs. Once the loop runs for 4000 times, the instruction now returns to the next instruction from where it was called. So the control will go to instruction number 12. Now it compares A with 255 and it again moves to the label repeat. So this is done, and also there is also one important thing that we need to know: why A is added with A51. So if we consider where we want, for example, if it is a staircase, we saw that the question specification was SW equal to 0, then the output must be a staircase waveform. So what we do is we divided 255 by 5 steps. Okay, so when you divide by 5, the answer is 51. So we increase every stage by 51 so that the lowest value is 0 and the maximum value being 255. So that is why we add A with 51. So after all the delay, this instruction from instruction number 9 to instruction number 12 keeps repeating until a staircase waveform is formed, and then the instruction again moves to instruction number 4 to check the value of carry, which is again assigned by port 0.0. So this is how the program works, and you need to give end at the last in order to finish your program. In this case, I have given my P0.0 to be 1, so I am getting a triangular waveform. You can configure your P0.0 to be 0, and you can also get a staircase waveform as well. If you can zoom in into this picture, you can actually see the different, you can see the precision with which the analog output is formed. For reference, you can refer to AT51 microcontroller and embedded systems by Masidi. You can also refer to linear integrated circuits by Roy Chowdhury to brush up your concepts on ADC and DAC converters. So in this module, you learned on what an analog to digital converter is and how to interface an ADC with microcontroller AT51. You also learned what DAC is and how to interface DAC 0808 with microcontroller AT51. This is Shailaja, Sanjana Balaji and Srimoyi Chakki signing off. Thanks for watching the video. Goodbye.